Welcome. It's good to see such a big crowd here. It's been a fun conference for me to be at just because I've been around cloud computing for a number of years, and nothing makes it real more than seeing lots and lots and lots and lots and lots and lots of users. So it's been a fun week for me. I've been through, in my career, 3 major transitions. We went from mainframes to RISC-based processors running Unix. We went through another transition from RISC-based processors running Unix to x86-based processors. And across each one of these transitions, you get the same thing happen over and over again. No customer says, hey, I want to have to learn everything from scratch, and I want to rewrite my app stack to run on a different architecture. Nobody ever does that. But the value equation was so damn good, you just have to do it. You just simply have to do it. You're crazy if you stay in the past. Cloud computing is in common with that. We're seeing the same thing. We're seeing the same transition. But there's one big difference, and that is the speed with which this transition is happening is phenomenal. I expected a quarter of the number of people here. I'm super excited by how fast this is happening. And I think what's really cool about this is when things are happening this fast, it opens up huge opportunities for innovation. And so we all have to learn more. We all have possibilities to do new apps. There's new ways of doing things. I kind of love it. What I'm going to talk about today is actually, it's an interesting thing. Years ago, before I was involved with cloud computing, I was involved with very, very high-scale computing. This is when you're running applications that are tens or even hundreds of thousands of servers. And years and years and years ago, I wrote down a set of best practices on how you get those services to run day after day such that they're never down. If you've gone to Amazon.com, you would be surprised if it wasn't up. You would be absolutely surprised. If you go to Google, you'd be surprised if it wasn't up. It's just these sites run like clockwork. And the reason why I wanted to present this material today is not because you're running sites that are tens or hundreds of thousands of servers, although some of you may indeed be doing that. It's because one thing's changed that wasn't possible before. It used to be that the techniques that I'm going to describe today were only possible if you were running many data centers worldwide, tens of thousands of servers. And what's changed is that's possible today at an incredibly low scale because of the tools that AWS makes available. And so I'm going to weave a pretty simple story where if you do, honestly, on the order of 7 or 8 things, you get an incredibly reliable result where you would be amazed if it ever went down. And it's embarrassingly simple. It does require focus, and it does require commitment to actually get it done, but it works. And so let me weave that out. I'll start with talking about the techniques. I'll give you a couple example failures one from industry and one from Amazon, just to show you some of the things that can happen. And then keep the app model in mind as I go through these failures, and you'll say, hey, we would have ridden through that. That would have been fine. And then we'll close up. First of all, I wanted to talk a little bit about just the facts. When I said to you, it really only takes 7 or 8 techniques to really get a reliable site, the biggest enemy of doing that is, well, things don't fail that often. It's super hard to invest engineering in something that doesn't really happen that often. I mean, when it does happen, you read about it, but it doesn't happen enough that you feel motivated. And so mostly, the reason why applications have issues is because they're underinvested, because there aren't enough faults. So let me remind you, let's look at how common faults really are. So in the disk drive world, we've got 4 to 6% failure rate. In the server world, we've got on the order 2 to 4% annual failure rate. That seems, it's a reasonable number. If you translate that to mean time to failure between failures, 3 years, the center of the server number, if you take the center of the server number, that's 292,000 hours between failures. That's like, why would I waste any time protecting against a failure that's going to happen once every 33 years? It's incredibly boring. I've got work to do. Why would I spend time on that? But if you take a 64,000 server data center, this is a the high end of a mid-sized data center, it's a good-sized data center, 64,000 servers. If you look at that and you say, well, actually, that would be 5 servers failing every day, 17 disks failing every day, probably independent systems. So we're talking upwards of 23 failures every day in that center. 23 every day, like clockwork, never a change. Failure is inevitable and actually surprisingly common. So it is worth investing in if you have scale. And this applies to infrastructure at all levels. It applies to servers, and there's so many of them, we all kind of buy the server numbers. It applies to disk. There's way more disks. We buy the disk numbers, but it also applies to switchgear, cooling plants, power distribution units. It applies across the board. The less of the pieces of equipment there are, the less common the faults are, and the less people tend to protect against them because you don't hear about as many faults. So let me show you a little bit on scale before we dive into techniques, partly because scale drives home the point, and some of these numbers are just fun. They're just kind of fun to review. So this is the one that I originally put this together a couple of years ago, and the idea behind this number was I wanted to find a way to talk about the growth rate of Amazon, and we're a little stingy sometimes in releasing numbers and how we're doing and things like that. We don't always want to talk about it, and it's mostly a good thing that we don't focus internally. I think it's a good thing. But we wanted some way to talk a little bit about some of the growth because we want you to understand this really is a big thing. This industry is big, and it's a good time to jump on board. And so the scaling number I originally put together is I said, well, I wonder how frequently. I first got to know Amazon in the year 2000. I said, how frequently do we deploy enough infrastructure to support Amazon in the year 2000? Did the math. It was every day. Like, it seemed impossible. We checked it every possible way. Nobody believed me. Everyone's checked this number. And in fact, it's been updated now to instead of being it's faster than every day, we're saying it turns out every day we deploy enough equipment to support Amazon in 2003 when it was a $5.2 billion business. This is a phenomenally big enterprise. It's an e-commerce site. It's all built on computing hardware. That's the rate we're rolling gear out. Think about that number. Forget about the innovation, forget about new products, forget about the release rate. Just think about getting gear from original design manufacturers through the logistics channel onto the shipping dock, delivered into the raised floor data center, make sure there's power available, make sure there's networking available, and get it online every day. That's supposed to be the easy stuff. And even that is actually kind of a big number. Let's look at a couple more data points. I remember when I started working in storage, I love storage. Database was where I got started back in the early days. And a big storage array was 3 racks wide, upwards of 1,000 disks. This is a very expensive storage area network. Think about this, 1 trillion objects in S3. If it weren't distributed all over the world and you were to pile it all in one data center, it wouldn't come close to fitting. You've got football field rooms, one after another, and you could not fit S3 in that facility. Wouldn't fit. It's phenomenally big numbers. These are numbers that I always like to pride myself. I think I get scale. I don't get these numbers. This is scale. Here's one more. We released this number a little bit earlier in the year. It was probably not even noticeable by some, but there's a couple things that are interesting. One is we have regions in 9 parts of the world, so we've now got the world reasonably well covered. Each region has multiple availability zones. Availability zones are one or more data center. In the Virginia area in US East, we have over 10 data centers of the size that I described to you earlier. So that gives you an idea. That is the biggest, but that gives you an idea. This is reasonably big scale. Okay, let's look at some of these techniques I told you about. Everyone on the planet knows this, and if you don't know it, I think if you think about it, you kind of agree. If you want the fifth nine, you must run in multiple buildings. You've got to run in multiple buildings. And People that sell data center space for a living talk a lot about availability, four-way redundancy, triple redundancy, but the truth is, the industry's been around for a long time. The high-value applications all run multiple buildings. They all do. Every financial app runs multiple buildings. And the reason is they need 5 nines. It's the only way to get it. So we all agree on that point. Where we don't agree is how to do it. So let's look at what the industry does. What the industry does is when you have, first of all, you use 2 data centers. That's the first standard. And you put one on one coast, and you put one somewhere close to the other coast. That's the way it's done. And if you think about it, that's awesome. What are the chances that the earthquake would hit both sides of the country at the same time? What are the chances the fire would spread from LA to New York? I mean, it's not going to happen. So that's the way it's done. And almost everyone does it this way, but Amazon doesn't. And so I want to show you why. The first test for this, it looks great. The first test for this is, would you be willing to pull the plug? In other words, would you disconnect one of those data centers? And the answer is always, are you insane? Never in my wildest dreams. And I claim it's because it doesn't work. That this form of redundancy really doesn't work. Let's look at what's wrong with it. Well, here's the biggest problem. When you commit a transaction to SSDs, you're running, in the TP50 case, 1 millisecond, maybe 2 milliseconds. In the outliers, heading for 10 milliseconds. If you were to synchronously update between LA and New York, that's 74 milliseconds. You're touching tens of pieces of networking gear along the way. If one of them is overloaded, just one, you drop a packet. If you drop a packet, you're 200 milliseconds gone again. You're a third of a second by the time you get that packet round trip in that case. Even if you don't drop a packet, it's still 74 milliseconds. That's a lot of time. You can't run synchronously between it. It just doesn't work. Nobody does it. It just cannot be done. It's unreasonable. It's too slow. You can't write a performance application. I mean, a disk drive, which nobody is using behind databases anymore, can do a poor disk drive can do 13 millisecond random seeks. And so this is not a practical number. So what everyone does is they run async. Fine. And it looks good because, hey, I'll commit to this LA facility, and then very rapidly I'll be sending over to New York. Just right there. All the transactions, they're almost arriving in real time. And so what could be better than that? But here's the challenge. If you have a failure, what do you do? It's hard to call. Because if you fail over to LA, you just lost a bunch of transactions. Because as much as you hoped that you got them across, there's a small tail that can't ship fast enough because you're shipping asynchronously. So you either lose transactions, that's not so good. It's not going to end the business. None of these businesses only have one record. There's audit logs, there's tracks all over the place. But it will take human beings 3 weeks to recover and get the system back to being consistent. And in the meantime, the customers may get incomplete results, missing transactions until that gets corrected. So it's not lost data, it's just painful. So you lose transactions is one model. The second model is you lose availability but you're not failing over. That's a tough call. Junior folks don't make that call. So what you do is you call all the senior engineers on the team. They get on the phone at the same time. It took 20 minutes to get them together. They say, how long is it going to be down for? Everyone says, I don't think it'll be down long. It's never been down longer than an hour. And so we speculate it's better not to fail over because it's not going to be down for long. Well, we're optimistic folks, and it probably is going to be down for longer than an hour because if it's a big high-scale site, if it really is down, something's wrong. And so eventually, it'll get failed over. It'll probably be down for 2 hours by the time that it's done, and then you pay the 3-week price of getting things back over time. That's why people won't pull the plug. That is a nasty place to be in. You don't want to be there. I've been on those calls. I get paid to be right, and those calls are terrible. They're just terrible because you can't be right. I mean, honestly, it's so hard to know what the right answer is. So this model makes for unhappy customers, and it makes for unhappy engineers. Second thing wrong with it is it's fragile. And the reason it's fragile is you're running all of your transactions against one cluster, and there's another cluster on the other side of the country that you can't fail over to because, well, you can, but you really hope you don't for the reasons I just described, which means that cluster is not exercised. And what that means is Maybe the load balancer has different ACLs on it. Maybe the network is under contention and that system doesn't have the capacity to support the load anymore, even though it did last week. Maybe the server software is a different version level. Maybe the sign-on database is at a different level. Maybe there's a latent hardware error that wasn't seen until loads hits. This model of running active-passive doesn't work. You need to have the load against both systems all the time. If you're not running it, it won't work. That's the first thing wrong with it. Second thing wrong with it is two-way redundancy is expensive. And the reason it's expensive is what's the maximum capacity that you can run at in steady state? It's 50%. And that's insane. And nobody runs at 50% because it means if you fail over, you'll be running at 100%. And if you're running at 100%, you probably aren't running. I mean, it's just, you won't run that high. So it wastes a huge amount of resources. You'd really rather be on a three-way redundancy model or higher. But a three-way redundancy model, I described the complexity of synchronously updating, of replicating software across a network. Well, if you're running three-way, there's more networking gears, you're exposed to more possible faults, the likelihood of them being inconsistent goes up yet again. It's kind of expensive because you have to have 3 facilities. It just doesn't scale very well, and so the model usually is practice 2, synchronous redundancy, and you get all of these issues. Let's look at what I think is the right way to do this. The Amazon model, and this is originally done at Amazon.com, but it becomes available in AWS as well, and it's tools that you can use to solve that problem in a very different way. And the tools that we make available are, instead of using regions as an overloaded concept, where regions, most people use regions for 2 reasons. 1, to be close to customers. 2, to get availability. And so it means that it's an overloaded concept. It means that it doesn't do one of those things well. We separate them. We say, listen, choose the region to be close to your customers, to be close to the data, or to meet jurisdictional requirements. Maybe you run in multiple regions if you have multiple constraints on your system. Choose it for the right reason. Choose it for that reason. Now you have a region. Now within a region, we need to give you reliability. What's the way you get the 5th 9? Multiple buildings. So we put multiple buildings inside the same region. And it turns out you can have them a long way apart. You can have them tens of miles apart, such that fire doesn't spread, different power, unrelated cooling systems. You can get them very independent. But if they're only tens of miles apart, that means they're a couple milliseconds apart, like a millisecond. Well, if they're that close, that's faster than an SSD. I can commit synchronously. Wow, life's different now. Now, when you commit to 3 data centers. All those problems just go away. Because you're committing to 3 data centers, if you lose one, what happens? Nothing. You have 2 copies instead of 3. Would you have the courage to pull the plug? Absolutely. Absolutely. And in fact, I'll show you that's what we do. You absolutely would pull the plug. And that's the proof that it actually works. Okay. Dave Patterson happens to be in the crowd. Dave Patterson was one of the inventors of recovery-oriented computing. It turns out that technique is really, really simple. It's deceptively simple, and it works. Now, I'm going to describe it in its simplest form, and I'm going to lie slightly, and then I'll come back and patch it up. So, in its simplest form, if you have a software system that's not working, something's wrong. Well, first of all, how do you know? Well, if you do not have a well-monitored site, it's never going to be reliable. So let's assume we get it well-monitored, really well-monitored. If the system's not healthy, you know it. And so what you do is, if it's faulty, restart it. If it's still faulty, reboot it. If it's still faulty, re-image it. If it's still faulty, replace it. And that is how big systems like search work. Well, you can do this in EC2. And replacing a server is start a new instance. I mean, you can do all of those operations. Is it a good idea to do that? Well, it is, because you can automate it. Does it solve every problem? Well, no, there's in fact a couple problems there's one problem it won't solve, and there's another class of problems where it will be a bad problem. It shouldn't be done. And here's a definition. So a couple definitions, and we'll talk about the 2 problems. Heisenbug was a definition originally introduced by Jim Gray, and what it means is there are a class of bugs that are, if you give an input to a software system, it faults under certain circumstances, but mostly it doesn't. That same input 100 times later works fine. What the faults are is maybe if this input comes in at the same time you're serving a networking interrupt, at the same time you're running over 85% load, at the same time there's a backup operation going on, then it falls. But otherwise it doesn't. The reason why Jim called it a Heisenberg bug is these bugs are deadly. If you instrument the system, you disturb the timing just enough, they will run beautifully. They will absolutely never fault. And so they're the most frustrating bugs in the world. Bruce Lindsay came up with Bohr bug as the converse of that. And a Bohr bug is you give it an input, it gives you a bad answer. You give it the same input again, still gives you the bad answer. It's always going to do that. And a Bohr bug would be handled very poorly using this technique. Because if you give it an input, we restart that server, it'll land on this server, we'll restart that server, it'll land on this one, the whole fleet will be down. That will be a disaster. So you need to avoid that. But turns out we're very good at testing systems and making sure Bohr bugs are out of them. It's the Heisenberg bugs that are killers. And so it's good at solving the problems that we're less good at resolving before you go into production, which is a nice thing. And there's some techniques to protect against this. The technique to protect against it is don't let the automata do more than a junior engineer would be allowed. If someone called me up right now and said, listen, I want to restart a server, I said, yeah, sure, fine. If someone right now called me and said, I want to restart 60% of your capacity, no, let's look deeper. Not going to happen. And so same thing with the automata, is don't let it do big things. Let it do small things. And what the beauty of this is 80% of the problems are small things. And so most of the load goes away, and you're taking away all the boring problems. Engineers hate boring problems. If you give someone 100 boring problems every day, my rule of thumb is about 1 in 5 will have an unintended consequence. They're bored, it's terrible work, about 1 time in 5, something will happen. Sometimes it's a net, sometimes they forgot to close the bug properly, sometimes it's big, like the entire data center goes down. I mean, unintended consequences, you don't know. It's just stuff happens. So don't give people boring work. This knocks off the boring work, they do the hard work, give them hard problems. People love hard problems, makes their job more fulfilling, and if it's different every time, you don't go in, oh, what's going on this time? You know, you can't. Okay, good technique. Here's another one that I fell in love with. I love this. A characteristic of software systems that I haven't addressed yet, but it's a characteristic that's common to every one of them. Show me a system that doesn't do this. I haven't seen it yet. And that is, I've told you how to deal with certain classes of bugs, but there's another class that's load dependent. And most systems, you give it input, it gives you an answer. You give it a lot more input, it slows down slightly. You give it a bit more input, it slows down a little bit more again. And then there's this cliff where it goes super exponential. Maybe the system starts paging, it just suddenly dramatically slows down. And you have to stay away from those cliffs, because that's the next thing to being just not delivering results at all. And you can't really know where that is unless you test for it. And so, what do? You test for it. Well, you don't want to test for it on the entire fleet, because if all of your servers go down at once, that's unfortunate. You don't want to do that. On the other hand, you don't want to test out of production because you can't trust the result. And so what you do is you put way more load, upwards of 2x the load on one server in the fleet. And what that does is, well, the fleet's pumping and going up in load and down in load and up in load. You've got one server that's going up in load and down in load faster, or higher. And what it means is it finds the problems first. The moment you find a problem, you can now hold the system below that load. You now know where the limit is. And you say, well, once I've done that, why would I keep doing the test? Well, the reason is software systems change all the time. And you'll keep adding features, and it will get worse, and you'll think the ceiling's here, and it will actually be here, and you will have a bad day. There's no way to know what's coming. And so, because this is always running, you always know where the limit is. Well, what do you do when you hit the limit? You're sort of screwed. Okay, I hit the limit. What should I do? Well, there's things you can do. In fact, there's a lot you can do. The first thing you can do is every system has some non-customer tasks. Every system's maybe re-indexing, maybe you're gathering statistics. There's things going on that customers aren't waiting for. And so if you're smart, you can say, okay, I can shut that off. And in fact, you can shut it off automatically. It's super easy to write administrative tasks to check a flag to see if you've got a problem right now. And so if you set that flag, all the administrative tasks shut off. That's a beautiful thing, because that actually can take away quite a bit of load. Usually that will solve the problem. If that doesn't solve the problem, the next level of protection is what I call degraded operations mode. And every engineer I've ever worked with says that, oh, well, yeah, sure. Other apps could have degraded operations mode, but my app does such important stuff. There's no, I either do it or you don't. And so what is, many people say, well, I don't know what degraded operations mode would be for me. I'll give you a couple examples. In search, the internet's full of, I think, 25 billion possible addresses out there, pages to index. But it turns out the vast majority of search results are the front 5 billion. And so, simply, one degraded operations mode is only give answers from the front 5 billion. Hardly anyone will ever notice that you didn't show the tail. The load just dramatically fell. No customer knows you're in trouble, and you ride through. And what would have happened is the whole fleet would have fallen. So, much better place. I ran an email team, and the email team said, okay, sure, it works in search, but that's an easy app. I mean, anyone can do search. I deliver email. And there's just, you either do or you don't. I mean, there's no way to... Of course there is. Absolutely is. On a great day, the internet mail is, 80% of internet mail is spam. And on a bad day, 98% is spam. So what do? You don't deliver spam. It means all the mail goes through really fast. And a couple pieces of email, very small number, that you misdiagnosed as spam, got delivered later. That is a beautiful degraded operations mode. We implemented it, and the problems went from almost daily to never. I just never got complaints. And we weren't doing anything better. We just exploited a characteristic of the workload. So these are hard to find, but they're all there. Final one is admission control, good of the many. You just don't let more customers in if the system's going to fall over. Another related concept is, this happened to the messenger system, and it's a good lesson, and that is, most systems have a more expensive, when you first interact with the system, it's more expensive than steady state operation. And by that I mean, in Messenger, the example was logging in is actually 10x more expensive than trading messages. Sort of makes sense. Okay, so what's that mean? Well, a fault happened once that actually took down the messenger fleet for a very brief moment in time. Very, very brief. And tens of millions of people jumped right back on and logged on, and it fell over. And tens of millions of people jumped right back on, and it fell over. And tens of millions of people jumped back on, and it fell over. And it turns out customers that want to send messages are very persistent. And so it stayed down for a long time. And the trick on this one is useful for two reasons. One is you have admission control on bringing the system back up. And there's two reasons you like to do that. One is you avoid the problem I just described. And the second reason is, if you're uncertain that you've really got a problem under control, it's super good to be able to bring one customer in and watch. And then bring 10 in, and then bring 1,000 in, and see how the system deals with it. And so it's useful for two reasons. Last one, this is one where this is unique to AWS. Anytime somebody has redundancy, of course they have all the servers. They don't have a failure and say, okay, I'm having a failure, I'm going to go out and buy a bunch of computers, a bunch of servers to back the system up. You already have them, of course. It'd be crazy. But because you can acquire resources so quickly in AWS, there's a temptation to say, well, what I'll do is, when I have a failure, I'll go acquire the resources. Because you get them so fast, it's just as good. It's not just as good. You really want to have all the resources that you need. Every EBS system, every EC2 system, have all the resources there and ready. And the reason for it is, getting resources is wildly more expensive and it's harder from an implementation perspective than just having the resources available to you. And so during a fault, when many customers, it could be many customers, are going to get resources at the same time, it's more likely you'll get exposed to resource contention at that point, and that will slow down your failover. And so this is tempting, and it's very unwise to not have the resources ready. And if you do that, it makes a huge difference. And many problems I've seen, you could have been ridden through without impact had the resources been there for sure. So strongly recommended. Here's a couple techniques that I think are super interesting. Basically, you'll hear a common theme from me, and that is, if you don't test it, it won't work. That's the common theme. Well, you got to test in production because no test system has sufficient fidelity. They're just not realistic enough, and they never can be. And so in this example, what Amazon does is it actually shuts down all of the capacity in one data center. Just shuts it off. And this is Amazon.com, not AWS. And the reason for it is they want to make sure that they can do it. And the only way you can make sure you can do it is you do it. And it's super hard to get started on this for the reasons I said. Can I pull the plug? It takes courage to do this, and you want to do it in the center of the day. Netflix does the same thing, or similar, it's a better thing, called the KS monkey, where they're constantly introduce bugs into the system. They're failing servers, they're failing messages, and it's super to do. And the reasoning behind it is faults are common enough that you have to protect against them, but unfortunately, they're not common enough that you get to test them enough. And so if you only get to exercise your error code after there's been a fault, then you get to do postmortem after postmortem after postmortem, figuring out how to get everything right. And in 10 years, it'll all be right. But your customers aren't happy for 10 years. It's not a good deal. And so this is a way to get the product right away. And you get to choose when your failures happen. You can choose them right in the middle of the day when all the engineers are there. It's unbeatable. I love this. OK, let me give you a couple example failure modes, just for fun, and just to test out the theories that I've been giving so you can say, oh, would that have worked? Here's one. I've taken the names off this because I feel for the person that wrote the postmortem. I've written a few in my life. They're hard to write. This one was written by the heart, from the heart, pardon me. I know what it's like. What they've done is they run in one data center, but it's an awesome data center. It's a 5.9 data center. It's quadruple redundant. It's gold-plated. This is an awesome data center. And so they've really spent. And this person's upset. He says the cause of the outage was an abrupt failure in our state-of-the-art data center facility. The problem was not just that the power failure happened. The problem was it happened abruptly, with no warning whatsoever. And all of our equipment went down at once. So disappointing. I've been there. It is. Well, you know what's going on here. If you have a power failure, there's warning. There is warning. Servers will run for 12 to 16 milliseconds at full load, and at light load, some of them will run for 50 to 80 milliseconds. It's not a great warning, but it's a warning. Second thing wrong with this is it doesn't work. I mean, it's single data center redundancy. You've got to use multiple buildings. And so it's a tough lesson. You have to talk to your customers about things that you hate talking to them about. And I get it. Let's look at a power distribution system. This is how a power distribution system works. This is how all data centers work at a high level. Utilities deliver high voltage. In North America, it's typically hundreds of thousands, over 100,000 volts. In this case, it's 110,000 volts. Delivered to a substation. Substation takes it down to mid-voltage, 12.7, 13.2. This particular facility is 13,500 volts, which is brought onto the premises of the data center. It's stepped down to 480 three-phase, and then delivered into the building. This is almost every center I've ever been involved with has that in common. In the building, you'll have a programmable logic controller that is sold by the switchgear manufacturer. It's essentially a small embedded computer that controls two breakers, the generator breaker and the utility breaker. And its job is manifold. The first job is never let both of them be powered, generator and utility, at the same time, because they're not in phase and explosive things happen. Second job is it tracks everything. And it makes sure that if it's a problem, the generator gets started, switches over to it, and does all the things that it's supposed to do. The reason why I chose this problem is I'm going to show you a fault that exists in every piece of switchgear that's sold, to my knowledge. It's the same in all of them. And because we run at extraordinary scale, we get exposed to more opportunities to see these things. And so the fault I'm about to show you has happened twice. So I'll tell you what happened. But because it's so insanely rare, this is the way all gear gets sold. It's kind of fun. That's why I liked it. Well, I didn't like it, actually. It was a little frustrating at the time. OK, so what happened in this particular instance that happened in August of last year is the mid-voltage transformer, 10 million watt transformer, exploded. And it exploded in a nasty, nasty, nasty way, and it sent a very large spike down through the system down to the utility breaker. The nasty spike was interpreted by the program logic controller as a direct short inside the data center, because that's what delivered that huge spike of current. And so because there's a direct short inside the data center, if they bring the generator online, the generator will hit that direct short, and it will probably destroy the generator. Generators are order $750,000 a crack. These are awesome, big V16, 4,000 horsepower wonders. They're truly a great thing, but they're very expensive. And so what these folks do is they've programmed the system to not expose that $750,000 piece of equipment to a potentially nasty event that it will not make it through. Well, that's not our goal. That's not our goal, but that you understand what goes on is there will be lawsuits, it will be messy, there will be people upset, and so that's the logic. And so what happened in this case is the start signal got sent out to the generator started up fine, the PLC will never close the generator breaker because bad things could happen to the generator, so when we arrive at the facility, it's idling, the generator's happy and idling. Unfortunately, when I was there by fluke, we were at a different facility. We arrived just as the servers were starting to come down because the UPS had discharged. It took us about 14 or 15 minutes to get there from another facility. Super annoying, super annoying. I could have written one of those more detailed. It happened all at once. Yeah. So the fix in this one's obvious. Because we get exposed to this and we know what's going on, we have multiple switchgear providers. They all do the same thing. We have gone through the PLC programming on all of them, and we do code reviews on all of our switchgear now, and we change this because that's not our goal. Our goal is the likelihood of there being a direct short in the data center that wasn't already protected by a breaker is very, very low. The odds of that generator being hurt are incredibly low. And when we weigh off the value of the customer server running versus the value of that potential to hurt that $750,000 generator, super obvious what the right answer is. And I think many people would come to the same conclusion, but the problem is they don't know. How do you know? You buy a piece of switchgear, you don't know that it's full of software, you don't know what the software does, and unless you actually have people that are willing, that have the appropriate skills, auditing someone else's software is super hard to do, and most of the switchgear manufacturers would never show it to you anyway. So it's just hard to do at smaller scales. So that's what we did on that one. Let's look at some infrastructure application lessons. Well, the first one is multi-AZ is absolutely the only redundancy model that rides through, allows testing, allows you to exploit your redundancy. I love this model. Super excited by it. And one of the cool things I think about AWS is because we're big enough that we can offer many data centers, many availability zones inside a single region. It means that this technique is available to every person in this room. I think that's a cool thing that wasn't possible before. I told you about the switchgear. It's now programmed to our own specs. Network resiliency and redundancy. I didn't mention this, but 2 is my least favorite number. Well, I guess 1 might be, but 2 is a terrible number. And the reason 2 is a terrible number is if you have one piece of equipment down for maintenance or you have a fault, the other one's just as likely to fail when this one's failing. You're exposed to the risk either way. You will get multiple faults occasionally happening on 2 redundant pieces, or you'll have one piece of gear down for maintenance while the other one will fail at the same time. I hate 2. It's super easy. It's almost easier to run n greater than 2 than it is 2 in the network. Having 2 huge, really expensive core routers or a small number of medium-scale routers, like 8, it's cheaper even. It's kind of ironic that that's the way a lot of systems get built. Okay, one last point. If you're interested in reading more and getting into more detail on this, I've written down every one of these tricks a few years ago in that paper at the bottom of the screen. The only one that's not covered is multi-availability zones within a region. And the reason it's not covered is I didn't really understand the model then. this is, I haven't seen that model done at scale before, and so that's not there, but everything else is there. So if you're interested in digging deeper, feel free to do it. I've appreciated having a chance to talk to you a little bit about this, and if you do have questions, I'd love to field them. Any questions at all? Thank you.